How's it going? This is PDX Mozzarella, and I'm going to be showing you Dijkstra's algorithm. So Dijkstra's algorithm uses nodes for pathfinding. And you can think of nodes as cities or waypoints or any object with a position. So they could be people just standing in a square or something. So the first thing we're going to need is a actual like a maze or something. So I'm going to create that on our grid. Alright, there we go. And the white lines symbolize walls or borders. So each space in the grid is 1, so it's a 4x4 grid. And we're going to be using that for distance. Alright, now that we have our maze, we're going to need nodes or waypoints or object positions, and there they are. Now, we're going to need to set every node to infinity, except for the starting node, which let's just go ahead and designate a starting node here pretty soon. I'm going to write infinity real quick. Alright, every node has infinity. And we will change this one to be our starting node. So we're going to change that to 0. And we're just going to mark that at start, so maybe an S. And we need a finish also. So let's just make this one the finish node. Okay, so we have our start and our finish. Every node has infinity except for the starting node. And you're supposed to add all these nodes into a unvisited list, but since we're just doing this visually, you can just kind of look around and see what nodes aren't visited. We'll show a visited node by placing a orange dot in the top left corner. Alright, the first step is, well actually it's the fourth step. The first 3 steps were to designate a starting node and finish node, that's step 1. Step 2 is to put infinity on everything except for the starting node, which we put 0. Step 3 is add all nodes to the list of unvisited nodes. So step 4 is to go through the list and see which one has the lowest number, which is the starting node. And the first question we're going to ask is this number greater than or equal to the finishing node's number, which is infinity? And no, it's not. If it was, we found the shortest path already, and we can just trace that. Otherwise, we're just going to keep moving on to step 5. So step 5 is set the current node to the lowest number, which is this number. We are going to ask for every node that's connected to this, which is any node that isn't obstructed by a white line and that it can see unobstructed pretty much. It's also going to be the first one that it hits in the row or the column. So obviously this node would not be connected to this because there's a white line. But this node would be connected to the one above it. So for each node connected to the current node that is unvisited, we're going to do some checks. So if this number plus the distance to this node is less than this node's number, then we're going to update this number and reference it back to the current node. So let's do that real quick. 0 plus 3 equals 3. 3 is less than infinity, so we are going to update this node's number to 3. Okay, and we're going to reference it back. Oops. Let's do it in, yeah, green's fine. And we're going to put the orange dots in the top left. Actually, let's go full top left. And this symbolizes that this is now a visited node because we went through all the nodes that it's connected to. Alright, now that would that'd be step 6, which is to check all the nodes, and step 7 is to mark the node as visited. Now step 8 is to run through steps 4 through 7 again. So if you're unclear as to what 4 through 7 is, I already wrote them down right here. So we get the lowest number of the unvisited nodes, compare it with infinity. It's not greater than or equal to infinity, so we set this to current. And we're going to do current node plus distance, which is 4. 3 plus 1 equals 4. Is less than infinity, so we're going to update this node to 4 and reference it back. Being that's the only node that it's connected to, we're done with this and we can move on to marking the node as visited. Same check. Is the lowest number greater than or equal to infinity? No. So we're going to mark this as current. 4 plus 1, 2, 3 equals 7. 7 is less than infinity, so we're going to update that number to 7 and reference it back. 4 plus 1, 2 equals 6. 6 is less than infinity, so we're going to update that number and reference it back. And being that's all the nodes it's connected to, we can now mark this as visited. Same check. 6 greater than or equal to infinity? No, so we're going to mark this as current. We're going to do 6 plus 1, 2 equals 8. 8's less than infinity, so we're going to update that number and reference it back. That's all the nodes it's connected to. We'll mark it as visited and go back through the list. 7, greater than or equal to infinity? No, so we're going to mark it as current. And we're going to do 7 plus 1, 2 equals 9. Update this to 9 and reference it back. That's all the nodes that this is connected to, so we can mark it as visited. Do the check again. 8 greater than or equal to infinity? No, so we are going to set as current. 8 plus 1 equals 9. 9 is not less than 9, so we're not going to update this or reference it back to 8. 8 plus 1 equals 9. 9 is less than infinity though, so we will update that number and reference it back. That's all the nodes that this one's connected to, so we'll mark it as visited. We're going to do the check. 9 greater than or equal to infinity? No. This isn't connected to any nodes right now, so we just mark it as visited. 9 plus 1, or sorry, let's do the check. 9 greater than or equal to infinity? No. So this is current. 9 plus 1 equals 10. 10 is less than infinity. So let's update that to 10 and reference it back. That's the only node that this one's connected to, so mark it as visited. We're going to go back through the checks. 10 greater than or equal to the finish node? Well, they're the same node, so yes it is. And we have found the shortest path. So through this lesson I've been referencing them back, and this is why. We just follow the arrows, and that's the path that we need to take to get to start. So an object at starting will go through this exact path to get to finish. I hope this helped out and kind of shine some light on Dijkstra's algorithm. If you have any questions, please feel free to ask, and if you feel I could have done this better, please let me know. All right, thank you.